In this video, I want to do an example of applying Newton's laws on a single object. In this case, I have some large block that's not attached, but just resting against one side is a smaller block. And I want to know how this large block is going to keep the smaller block from falling. So the smaller block has some mass m. And so I might ask, is there any speed at which I can move this object to keep this small mass falling? So if this large mass moves very quickly, how fast does it have to go at constant speed to keep the mass from falling? The first is to choose an object, so I'm going to choose the small mass here. That's what I want to keep from falling. I want to analyze the forces then on that object. There's going to be the force due to gravity. The only other object touching it is the large mass, so there's a contact force between the large mass and the small one. So I'm going to break up this contact force into the normal force and then the friction. And I'll call that F sub small f. And nothing else is in contact with the small mass. I'm ignoring air resistance. That's kind of key, isn't it? My next is to put them on a free body diagram. So I want their force due to gravity, which is towards the center of the Earth. The normal force is perpendicular to the surfaces. It points from the agent to the object, which is, this case, the agent is the large mass. The object is a small block. That's the normal force. And next is the frictional force. So the friction acts in a so it's static friction. Since I want to keep the system from moving, I want the condition where the two masses are at rest relative to each other. So in our contact force model, the force due to friction points in the direction opposing the motion that the object would move relative to the agent if there were no friction. If there were no friction, we would believe this mass would fall. So the frictional force would be in the opposite direction. So that means that the frictional force is up. So there are my three forces on my free body diagram. I need a coordinate system. I'll put my coordinate system up here, just so it sits out of the way. And so I'm going to have the positive x going to the right and the positive y to be up. With my coordinate system, I can now look at the vector sum of all my forces. Gravity, and it has a 0 magnitude in the x direction. It has a magnitude of mg in the y direction. That's an entire magnitude, and given my coordinate system, that's negative. My magnitude's positive, but my component is negative. So next is going to be the normal force. It has its entire magnitude, which is positive, along the x, and that's 0 in the y. My force due to friction has 0 in the x-axis, but now it has a magnitude equal to the coefficient of static friction times the normal force in the y-axis, and given my coordinate system, that's positive. The vector sum of all of these forces is the mass times the acceleration. Now I want the condition where the block is not falling. The y component of the acceleration is 0. So then there may be some acceleration in the x direction. This vector sum equal to my mass times acceleration now gives me some relationships between my parameters. So I have that the normal force is equal to mass times the acceleration, and then I have that the static friction times the normal minus mg is equal to 0. So the first thing I recognize, I can answer my first question, which is there any constant speed where the mass does not fall? And the answer is no. At any constant speed, then a is 0. If a is 0, then n is 0 from here. And if n is 0, then the frictional force is 0 here, and you simply have the force due to gravity and it falls. How must the large mass accelerate the block such that it stays? Well, it has to maintain a normal force to maintain that acceleration. And so we can solve for n and put that in this expression to eliminate n, and then we can solve for the acceleration necessary so that the block wouldn't fall. And so this becomes mu sub s times ma minus mg is equal to 0. The m's cancel, and I get a is equal to g over the coefficient of static friction. So that's the acceleration must be applied to the block to keep it from falling.